Good morning, everybody. Thanks, Steve, for the introduction. It's actually, just to start on the first slide, unfair that I put just my name up there, because I could have a huge list there I'll read later on. This is, of course, not a one-man show here. Okay, as you might know, Bruker has started developing a commercial preclinical MPI scanner. Here you can see our Ettling premises where the scanner is being installed. So we're working on it. Regarding the state, we're currently in the process of integrating and testing it in our facilities. Down here in the basement, the former cafeteria, which we gave up. The hardware is currently 99% complete. Hopefully it will be 100% when I return to Ettlingen. I'm waiting for the last final parts. Our different factories are preparing the series production, so that is in starting, and we are really proud and happy that MPI will really complement the palette of other preclinical imaging modalities that we have on offer right now, such as MRI, microcity, SPECT, PET, X-ray, and optical. So MPI really is a very welcome addition to this collection. Now, why are we doing that? First of all, MPI is a really smart idea, and we love smart ideas. But of course, there's another. MPI has the potential for many applications. And this is a sheet that I actually inherited from Michael Kuhn from Philips, so thank you for that. To list some of the visions that people have and ideas that are floating around what to use MPI for. And if you look through it and look to the conference program, you really see that these items are being addressed part by part, and people start scratching into these issues. So we think MPI can have a bright future with all these potential applications. But we may wonder why it's taking so long to get there, and here's my idea about that. If you look about for the available scanners worldwide, there are actually very few needles around here. We are at Berkeley right now, very nice scanners installed here, we saw them yesterday, and all the remaining other scanners, please correct me if I forgot one, are in Germany. Hamburg, where MPI was invented in 2001, Lübeck, very nearby, then more recently Braunschweig and Würzburg. And if you think about it, all these scanners are installed in laboratories by really MPI enthusiasts, technology enthusiasts. They are operated by the very people that designed and created these scanners, namely physicists and engineers. And so the workhorse is driving the technology forward. So we hope to add Ettling to the list very soon, but maybe in a slightly different focus, and that's what I'm going to talk about today. If we think about the open research areas that could be addressed in the future, I thought if there might be work with the MPI application protocols. For example, what's the right dose of the contrast agent to apply? Would you like to inject once or multiple times, or would you aim for a steady state protocol? Where to place the field of view? What resolution to aim for? Multiple field of views? Many questions that need to be addressed to create viable protocols for MPI imaging. Of course, there is a huge range of new contrast agents to be tested. Just look around at the posters here and you see, get an idea that there's a lot to be explored. Then, of course, there's work on reconstruction techniques going on. X-based, system function-based reconstruction, model-based reconstruction, different ways of acquiring system functions, of calibrating the scanners, and so new technologies, faster reconstruction. A lot of work needs to be done just in the math area. And again, we have presentations on that here. Then, of course, there's a huge area of diagnostic interventional imaging. I mean, in the end, MPI should become a tool for the radiologists and for the clinical routine, but we need to test it and to verify that we will fulfill these promises. We have to compare MPI to other modalities. Under comparable conditions, what's the best tool for a given task? Where will MPI fit into the entire game? And finally, work on the sequence design. If we want to go for large field of views, if we want to have optimal resolution, what are the right protocols, how to design the scanners? Just single line scanning with shifting the line, plane imaging, 3D imaging. There are different techniques available already, and at the moment don't have a clear view what is the ultimately optimum sequence, or if there is actually an ultimate optimum. So my conclusion is that we clearly need radiologists and non-technical researchers to get more access to MPI scanners. Actually, it's not only my opinion, it's also the opinion of the German Research Foundation, which is funding the installation of new scanners in Germany for application-oriented research. So there's clearly a need for an application-oriented scanner that is more readily available. But if you think about it, probably such an application-oriented scanner has different design goals than the currently available machines. At least it's my thought. And if we look at various parameters, for example, the hardware layout. I mean, I saw these beautiful scanners yesterday evening. And if you think about it, when you're building your own API scanner, you want it to be very open in design. You want to change every day, improve it, make it better, test out new things. So it must be very open and very flexible for redesigns. That is your design goal if you build your own scanner. Whereas an application-oriented scanner is nothing that you want to mess around internally. It's just to work and be easy to access, easy to work with. It should be very robust, get the same results every day, be stable, be safe. So it's quite different. You want to have a more closed design probably. And for installation, it would be actually helpful to have it in huge integrated components rather than many small parts. So that's also different from the currently available scanners. It's not that one thing is better or worse than the other, it's just different. Regarding the reproducibility, of course, if you build your own scanner, you're happy with that. You don't want to have build it twice, because your next scanner will be different and better, of course. Whereas if you have an application-oriented scanner, you want to have it multiple times, so different sites can compare the results very directly. So that's a different goal as well. Regarding the user interface in the broadest sense, not only regarding software, but handling. If you build your API scanner in your laboratory, you can probably afford to put the animal on a piece of cardboard. And you can afford to switch on 10 amplifiers in the correct sequence to get the machine working. But this is really not appropriate for an application-oriented machine. That should be push-button operation. And such a developer will spend more time to get that right. Regarding the versatility, if we look at the currently available designs, you can really see how people are systematically varying the design goals to achieve optimum performance of certain parameters. Go for the highest gradient strength, go for the highest resolution, go for the highest sensitivity, go for the highest frequency. So you can explore different parameters that can be optimized or driven to extremes. Whereas a scanner with broad availability should not go to extremes in any of these parameters. It should rather be a robust platform that makes everybody a little bit happy. Finally, compatibility. I mean, if you're an MPI enthusiast, you want to get the best possible MPI images. Whereas if you're working application-oriented, you want to compare it to other modalities. So you want to move your animals from one scanner to the other one, compare the data, and have the option to bring them together and to fuse the images. And finally, regarding software integration, I mean, proper software integration is a large task. It takes a lot of time. So you wouldn't waste too much on that if you're designing a new scanner every 2 years. And whereas a commercial scanner, of course, needs sort of a robust platform for experimenting afterwards. So as a conclusion, an application-oriented MPI scanner has quite different design goals and challenges to face than the currently available designs. And again, this is not better or worse, it's just different. That's my argument here. Okay, how do we start with the development at Bruker? The mission or the goal is to provide access to the MPI technology for a broad range of application-oriented research. And this is really what we want to achieve in the end. So we are very happy to have a very good cooperation with Philips, and we are very grateful for the support we are receiving from there. So we started from the preclinical MPI demonstrator that Philips designed and implemented, and brought it together with Bruker's knowledge of preclinical MRI scanners. We put all the components together in an integrated redesign to make sure that everything fits well together, and that's the way to end up with the Bruker preclinical MPI system. And this is what it looks like. The technical data here. We'll just go through it very briefly. We've based the acquisition hardware and control hardware on the Avance 3 platform that Bruker is using in many thousands of systems around the world, NMR systems, MRI systems, even mass spectroscopy systems. So we're building a familiar technology in that area. We're using the PowerVision software, which drives hundreds of preclinical MRI scanners, and we really found that MPI could be integrated very well into the workflow provided by the software. The scanner implements full 3D imaging. That means 3 excitation axis, 3D drive field, in addition with shift or focus field coils to access a large field of view, which is actually necessary because of 12 centimeter free access. So the scanner will be suitable for mice, rats, guinea pigs, and even rabbits.
which was one of the design goals where we're going for a little more than what's currently done. The animal handling is compatible with our MRI scanners. We've integrated a calibration robot if you want to work with system function acquisition, and we provide interfaces for animal monitoring and infusion pump. Maybe one thing that probably stands out a little bit, we have provided the scanner with a scalable selection field and designed it with a resistive magnet, so you can zoom in or zoom out of your field of view, which I think might be an interesting research area of its own, and could come very useful. Okay, here's a little block diagram, and don't be afraid I won't go through it in detail. Just show you the major groups. Here's the field generator, a 7-channel magnet basically. Here's the resonance circuit, which is enclosed in these boxes, and the detection system, the filtering, is enclosed in this part here. All the amplifiers are in the group here, and really that part up here is what we reuse from MRI. In fact, we didn't design a single new component of digital control. We used this MRI sequence controller to provide precise timing for MPI. We used the digital pre-emphasis process to actually drive the drive field, the real-time control. We use a radar controller to control the focus field and the static field. The gradient interface to control all these amplifiers and provide the correct current. And the receivers have been nicked from Fourier transform mass spectroscopy and just the perfect data sheet for MPI, so no new development in that area either. Okay, of course you may be curious to take a look into the scanner, so I've provided some photos or drawings what the inside looks like. We start with the drive field. It's an oil-cooled design with a 12 centimeter inner diameter, and 3 channels that might provide up to 20 millitesla. Around that is selection field, a scalable selection field made from copper hollow profiles, water-cooled up to 2.5 Tesla per meter. Actually, I should have said it's run by a 500 amps current, quite a lot actually. Then we have the shift coils in XY direction in the plane, and additional shift coils in the vertical direction. Again, 500 amps, quite a lot, water-cooled. The whole thing is including a cubic shape or cubic housing. And you can see it's actually rather compact, 50 by 50 by 50 centimeters, it's not large. And, well, this is what it looks in reality installed on the scanner. Some more details. As I said, everything needs to be boxed and integrated in huge components. Here you see these boxes that contain the actual resonance circuits. Very compact, just a single box that houses all the components, lots of capacitors, coupling circuits, and filters, and so on. Here's the electronics, again not very large, sequence controller, the gradient interface, and the detection rack, acquisition rack. Here's the user interface from Paravision with integrated viewers and a controller card where you can fit all the parameters that you want to operate. We hope to make that a bit more approachable still. Well, when I said push button operation, really this is the single button to press to get the system on. There's another button to switch it off, and if you're really urgent, there's another one to turn it off, but you don't want to use that really. And the rest is controlled by a single workstation here, so it looks rather, well, convenient. And as I said, we have taken care to integrate the animal handling or make the provisions for animal handling. You need an infusion pump in many cases that you can call by serial interface, triggering fiber optic lines for the monitoring equipment. And an important point that I'll come to back later is that we provide DC sockets here for powering these front-end equipment. That's actually quite crucial, and I'll show you in a moment why. Well, that's our technical room. We actually need quite a lot of cabinets right now to house all the amplifiers, but the good news is there's some space left in them, so if you want to add some equipment, you'll fit it in. Okay, so that's what the machine looks like. I was not talking about promising not only talk about the chances, but also about the challenges. Of course, there are challenges in building such a machine, and I don't want to bother you with all the bureaucratic things that have to be addressed when you really want to bring a scanner to a market, but rather give you some insight, because many of you are also building your own scanners, what experience you can have in the lab. For example, if you really have to handle 500 amps, the cable become rather cumbersome to handle. You can see Jochen here trying to install these cables, which are really messy, and you know what you've done in the evening when you mounted them. Then one issue that was a bit unfortunate for us, of course we have a huge stock of filters in our production for MRI, and it turned out that we couldn't use them because 25 kilohertz is just very different from the hundreds of megahertz in your MRI scanners. So a lot of even simple components had to redesign, re-engineered and implemented. So our list of partners has grown significant when we started designing MPI. Then, of course, you have to review every component. Sometimes it turns out that it looks very nice in the drawing, but when you actually have it in your laboratory, it turns out that the openings are just a lot smaller than they appear to, and you have to send them back and re-engineer the boxes in the end. Finally, surprisingly, cables do only conduct current. Sometimes they also conduct oil. And again, when you learn that, take a component, ship it back to the factory, and have it re-engineered and the problem solved. When it was talking about the switching power supplies, they are really evil. I mean, in our scanner, you can have all the monitoring equipment nearby, but if you put such a switching power supply near your receive coils, you suddenly see that you don't see anything anymore, because they generate such a lot of noise in this low frequency spectrum that you really have to avoid them. This is the reason why we provide these 12 volt DC sockets to drive the equipment. So to sum up here, lessons that we had to learn when working on the scanner, MPI and MRI are really quite different when it comes to engineering, so it requires very different engineering, manufacturing and testing expertise than MRI. The component reuse is really restricted to the digital electronics, but of course that is an advantage as well if you can use that. Every detail matters, even small details can get you wrong in your scanner, and you actually have to take significant investments into manufacturing and testing equipment to be able to produce these MPI scanners. Now, what else are we doing at Bruker? Just to give you a little insight, we had these talks by Jochen yesterday, which gave you some ideas already. We're working on the hardware optimization. Of course, we want to bring forward the technology. We work on the system integration, make it more compact, more approachable. We work on alternative scanner designs, as Jochen told you yesterday already. We want to integrate with other modalities which you have available in Ettlingen. And we work on reconstruction techniques, and there will actually be a talk by Alexander Weber today, and he's a poster outside as well. We're really grateful to have support by a grant of the German Federal Ministry of Education and Research for doing these new things. Okay, to sum up, I'd like to acknowledge some of the people that have contributed to the work. So this has become a huge list. Foremost, I'd like to thank Bernhard Leich, Jürgen Weizenegger and Ingo Schmale, who have really been supportive in getting us going with the scanner. And they've actually visited us a couple of times in Ettlingen to solve some thorny problems. But then I'd like to acknowledge Holger Autz and Lothar Mattis, who designed the magnet and the entire outside of the scanners. Then our colleagues in Switzerland provided the low field electronics, which was a challenge for them as well. They are RF engineers. Some of them said, well, it's like working in DC if you're working at 25 kilohertz. So it was a new field for them as well. Our French colleagues provided the drive field and really invested time in researching the correct manufacturing technology for that, which is a challenge, to be honest. And then in Ettlingen, we have quite a lot of colleagues. I'd like to mention Jochen Frank, who has been a really great colleague to work with. And Tobias Knopp, who we all know, who has unfortunately left us and also left the field of MPI. We're very sorry about that. But he has been working single-handedly implementing reconstruction algorithms in the Paravision software stack. And many, many other colleagues, as you can see here. Now, to finish off, people sometimes ask why Bruker is doing all that, whether we believe in MPI, and will it flourish in the end? Of course it does. But why can I say that? Our background is, of course, MRI. So what can we learn from MRI? MRI was invented in the early 1970s. I think the first paper from Mansfield was in 1973. After MRI was invented, it took about 5 years to the first preclinical images to appear, actually in vivo images. So pretty fast. And the first commercial scanners started to appear in the early 80s. So just after 10 years or so, 9 years maybe. And well, this is what the Bruker scanners of those days looked like. Huge machines with, well, Star Trek consoles of the 60s maybe. These were the images of those days. I mean, people were really, really happy to have these kind of images there. But by today's standards, I mean, they took several hours to acquire, 1 animal per week maybe. The construction several hours. And still people were very happy to do that. But having these commercial scanners available actually boosted the field 1985 saw the invention of the flash sequence, which really made fast imaging a possibility. In the 90s, functional MRI emerged. So instrumentation and new ideas for how to utilize them increased hand in hand. And today, of course, we have lots of different scanners of any size and power available. The images are just fantastic. You can get from even small animals. So, and of course, I don't need to tell you, MRI is a routine technology in clinical applications today, with a broad range of things you can do with it. So let's put the MPI time frame underneath. MPI was the first publication was in 2005, although we know that the actual invention is a few years older than that. The first in vivo images were published in 2009, so again we are on track, on schedule with that. The first commercial scanners are going to appear this year, so again we are on track. Here's what they look like. This is the image quality of the early 2010s now, thanks to Philips for the image here. But again, if you look at the MRI time frame, you can see this is just the beginning of an exciting story that we are all part of now. So what will happen in the next few years? Of course, I don't know. I have no magic ball to look into, crystal globe to look into. But maybe we're getting better with the resolution, sensitivity, field of views, more larger range of contrast agents, targeted contrast agents, molecular imaging. Sorry. So there's a lot to be done in the next few years, of course. So what will the scanners of 2040 look like? Well, I found one picture here. You can barely see there are two people here, probably Bernhard Gleich and Jürgen Weizenegger, working on the 100-channel 1 megahertz drive field that they're mounting on the pole shoes of these 50 Tesla per meter magnet here for preclinical imaging of elephants, I suppose. I don't know what the images are going to look like, so I have a question mark here. But I invite you all, we can all come together and fill out this gap here and make exciting images in the next few years and decades to come. And we're very happy to be part of the story. So I think MPI is a very bright future, and we strongly believe it will become a routine imaging technology, and in particular by the availability of many more tracers, will approach a large field of possible applications that will sign a bright future for MPI. With that, thank you for listening.